Hello friends. So in our previous lectures we have been attempting to extend the assumptions or the conditions that render us the schematic representation of the mechanical behavior offered by the metals and alloys. So when we want to describe the mechanical behavior offered by this category of materials, we consider a graphical representation that involves the mechanical condition that we impose and the response offered by the material. So the mechanical condition that we impose generally is associated with the uniaxial tensile loading, and the response that we quantify in the graphical representation is the change in the longitudinal dimension of the material. Now in the previous lecture we have extended first the assumption of the change in the longitudinal dimension, and our consideration of Poisson's ratio or Poisson's effect helped us include another change in the dimension that we observe when we impose a uniaxial tensile loading, that is a lateral dimensional change or a lateral change in the dimension. Now secondly, we were also able to consider a more complex form of mechanical condition in addition to the uniaxial tensile loading, or when compared to the uniaxial tensile loading. This we refer to as the biaxial tensile loading, and we also moved away from biaxial tensile loading in our previous lecture to tri-axial tensile loading. Now, depending on the nature of the mechanical condition that we impose, be it biaxial or triaxial or uniaxial, the response offered by the material, it varies. The way we need to express the response offered by the material gets more and more convoluted or more and more complex. So depending on what is the nature of the mechanical conditions, in all these cases, in case of uniaxial and biaxial and also in case of triaxial, in all these cases what we are essentially imposing is the same nature of loading, that is we are imposing tensile loading. The nature of the load remains the same, but we are including additional dimensions to it. We are including additional loading directions, and correspondingly the response offered by the material also adopts a convoluted form. Now we saw that in case of triaxial tensile loading, the response offered by the material, it can be categorized as direct and indirect responses. Of course, this categorization is for our convenience, and the direct responses is along the direction of the loading, and the indirect responses is perpendicular to the direction of the loading, and this can be represented by appropriate notations. We use two subscripts for the epsilon that is conventionally used to describe the strain. Now in the case of direct response, we end up having, or the epsilon assumes the identical subscripts. In case of indirect response, in case of under triaxial loading, the strain or the epsilon assumes dissimilar notations. So we saw that in all these three cases, the most convoluted or most complex one is the triaxial tensile loading, and the triaxial tensile loading, the response offered by the material under triaxial tensile loading requires 9 different strain components to give a comprehensive description of the response offered by the material. So when you want to comprehensively describe the response offered by the material under triaxial tensile loading, you can represent it in this manner. So in each of these, these notations and the subscript have a specific representation. The first subscript, it denotes the direction of loading. The second subscript, so this denotes the direction of load, or rather this denotes the direction of the strain. And the second subscript, please don't make that mistake which I just now made, that is the first subscript, it denotes the direction of the strain. The second, it denotes the direction of the loading. So it is possible for us to represent this response in this manner, where we are able to encompass all the 9 components of the response offered by the material under triaxial tensile loading. So along the diagonal we have the direct responses, and the non-diagonal elements, they form the indirect responses. Now what essentially we can do is, starting from this representation of the strain, it is possible for us to now represent the strain offered by the response offered by the material under both biaxial, the uniaxial tensile loading. The thing is pretty simple. If you know to describe the strain under a convoluted case, under a complex condition, from that representation we can simplify the response offered by the material for our given case of biaxial or uniaxial tensile loading. If we know how to represent for the complex case of triaxial tensile loading the response offered by the material under triaxial tensile loading, then biaxial and uniaxial is just a simplification of it. For instance, if you consider biaxial tensile loading, all we need to do is the strain along the z direction or the load along the z direction will assume the value of 0. So therefore the entire matrix, it shrinks in rank or it shrinks in size. And if we even reduce and consider uniaxial tensile loading, we will no longer require matrix, we just need 2 elements. So what essentially we have done is we have considered all these different loading conditions. We have also seen what are the different responses offered by the material and what are the how we can express it meaningfully. Now the reason we have considered all these 3 loading conditions is primarily because very rarely, apart from the experimental conditions, very rarely we observe a single form of loading in a real life application, a single form of tensile loading even in a real life application. So therefore, to move away from just the theoretical consideration, we have now considered or we have now included the complex form of tensile loading. Now even though we have increased this complexity associated with the tensile loading, the way we have considered the response of the material to these different tensile loading has been of similar form. Meaning, even though we have been considering or extending our assumption of the loading condition, even though we have been extending our assumption of generalizing our assumption of or description of the mechanical condition we impose, the response offered by the material, we have been considering it along a specific direction only. So even though this representation assumes 2 different subscripts, so these representation, even though they are characterized by 2 different subscripts, the first subscript x or y or z, this first subscript, it focuses on or it aligns itself in so it aligns itself along a specific direction. So what we are essentially doing is we are considering a specific direction and then we are considering the strain offered by the material in that direction. So that is essentially how we have been representing the response offered by the material irrespective of or for the different mechanical conditions that we have been imposing thus far. And we have been able to rather sum up the strain offered in a specific direction. For instance, we have been able to sum up the overall strain along a specific direction. So for instance, we have been able to sum up the overall strain along the x direction. We saw it assumes the expression is of this form, wherein the stress that brings about the strain assumes it takes the place of the first term, and the second and third terms are the stress that offers the indirect responses. So this is the generalized form of the overall strain along a specific direction under triaxial loading condition. The first term is the one that offers the direct response, the second and third terms offer the indirect responses. So we can express along the y direction, the expression adopts a form like this, and along the z direction it adopts a form like this. The reason we need to focus on the form is because we don't then have to worry about memorizing it. So I personally don't remember anything. It's just I understand how the form is, so therefore based on that understanding I'm able to write this. Now, even though we have been able to describe the strain along each of these directions, the complete strain of what will be the resultant strain along a specific direction, still we are focusing on the individual direction of x, y and z. Now, what other way we can describe the response offered by the material is by considering the system as a whole, by considering the sample as a whole. When we say we consider the sample as a whole, what we mean by that is before testing, before imposing the mechanical condition, the system as a whole has a volume of say V. Now after imposing the mechanical conditions that we have considered, be it uniaxial, biaxial, triaxial, depending on the mechanical condition, there would be a change in the volume. Now what we want to do is, instead of describing the response exclusively in terms of the strain along a specific direction, exclusively in terms of the strain, essentially it means a dimensional change along a specific direction. What we want to do is, we want to describe the response holistically, comprehensively, based on the change exhibited by the entire volume of the material. So that is what our intent is. So when we are able to do that, when we are able to achieve it, then we can no longer focus on a specific direction. Then in that case, we can comprehensively describe, can holistically describe how the volume of a material changes under a given loading condition. Now, in order to do that, let us begin by considering or describing generally what are the different factors that govern a volume of a given material. So if you consider a volume of a given material or a given sample, its volume is primarily governed by the dimension along the specific directions. So for a three-dimensional case, we have assumed the dimensions or the coordinate system of x, y and z axis. Now when you want to describe the volume of a sample in this three-dimensional framework, the volume of the sample essentially unless otherwise we are considering a complex shape, if we are considering a simple sample that we will be using, a straightforward sample that we will be using for tensile testing, be it uniaxial, biaxial or tri-axial, the sample usually is of the cylindrical form or a form that we can easily associate with. So therefore, the volume of the sample depends on the dimension along the x-axis, dimension along the y-axis and the dimension along the z-axis. So we are considering a three-dimensional case. So we have introduced a framework to describe this three-dimensional case. So the sample in this three-dimension, the dimension of it, particularly the volume of the sample in this three-dimension, is influenced by the dimension of the sample along each of these three directions. So the three-dimension is described using a three-dimensional framework, three-dimensional coordinate system. Now the volume of a sample in this three-dimension is dependent on dimensions along these three direction that characterize the three-dimensional setup. Now let us see how we can describe the change in the volume of such a system. For the simplistic case, we can treat or if you want to have a convincing understanding of what this Lx, Ly and Lz are, we can consider the Lx to be length, just to describe or attribute a name to each of these variables. The Ly could be breadth or the width, and finally the Lz could be the height. Now let us assume or let us try to describe the change in the volume when we are imposing a triaxial loading condition. So the reason we begin with triaxial loading condition is because we have seen that once we are able to describe a response for a complex loading condition, then we can simplify that representation to render the response offered for the biaxial and triaxial. So non-complex loading condition, we will be able to express the response when we know how to express the response for the complex loading condition. It's just the simplification of it. So now let us consider a sample, a three-dimensional one, is experiencing a triaxial loading. The change in the volume owing to this mechanical condition that we impose can be expressed using a partial derivative rule that we often associate or we often see, we observe in the thermodynamics. We use this rule very often in the thermodynamics. So what it entails is that we want to separate the change in the volume in response to the change in each of these dimensions. So we have three dimensions along the x, y and z axis, and what we want to do is we want to express the overall change in the volume by considering the change in the volume in response to the change in each of these dimensions. The way we can write is the change in the volume as the change along the dimensions of the change along the x axis when the dimensional change along the y and the z axis are constant. So what essentially the first term indicates is we are considering change in the volume as the dimensions along the x axis varies, assuming that the dimension along the other two axes are constant. So this mode of representation, in this case these two terms are constant, and we are considering the change in the volume as the dimension along the x axis changes. Now we are assuming that all the three dimensions are changing, so we need to also consider the change in the volume as the dimension along the y-axis changes, under the assumption that the dimension along the x and the dimension along the z are constant. In the same way, since there is also a change in the dimension along the z-axis, we need to include that as well, assuming that the other two change in the dimensions along the other two directions are constant. So we end up with this relation here. So what essentially we have done is, we have split the overall change in the volume of the material into three different terms, and we have considered the change in the volume with respect to the change in the dimension along a specific direction. So the first term, it indicates the change in the dimension, so change in the overall volume with respect to change in the dimension along the x direction, assuming the other two dimensions are constant. Second term, change in the volume with respect to the y direction, assuming the other two dimensions are constant. Third term, change in the volume with respect to the change in the dimension along the z direction, assuming the other two dimensions are constant. So this is essentially what we done, and we have done, and we have now an expression that describes for us the overall change in the volume dV. Now, when you consider the change in the volume, this term alone, that is the dV and dLx. So when you consider the combination of these two alone, what we have is, we have volume and one of the dimensions, the dimension along one of the direction, and we are considering the change in the volume with respect to the dimension along one of these, one of the principal direction or one of the primary directions. So when you consider a volume of the substance and a dimension along a particular direction, supposing, let us assume for instance a simple cube such as this, and let us assume the volume, the original volume of the cube is V naught. And now what we have is, we have already introduced our coordinate system. So this is x, y and z. Okay. Now what essentially we are trying to do is, we are trying to increase the dimension along the x-axis. So Lx we are trying to increase. So and we have assumed, so we are considering this term alone here. So in this term alone here, we have assumed that the dimension along the y and the dimension along the z are constant. So in this case, we are increasing the dimension along the x-axis alone, and correspondingly your volume increases. So when you consider the relation between the volume change and the dimension along the x-axis, so let us assume it to be a cuboid. So in this case, the volume V naught will be equal to Lx, Ly and Lz. And now what we are changing is, we are changing the Lx alone. So this is the only variable and these two are constant. So what it essentially means is that the volume of your cuboid is directly proportional to the dimension along the x-axis. So let me repeat, what we have done is, we are considering a simple system, a cuboidal system. We are expressing its volume V naught is the product of Lx, Ly and Lz. So dimension along the three different directions. Now the dimension along the two directions are constant, only one is varying. So we can use this proportionality symbol to indicate that the volume is linearly proportional to the dimension that is increasing. So when you plot the volume versus the dimension along the specific direction, so volume versus Lx, what you observe is there is a linear relation, and this means that this has a specific form. So what we have is a straight line, and there is an expression for the straight line. So volume is directly proportional to Lx, and if I introduce a constant here, say k, so this is what, so in this here the constant of proportionality is the product of Ly and Lz. This is for cuboid case. Now for generalized case, this will be the expression. So this will be the expression of how the volume is related to the dimension for a three-dimensional setup. So this is for a cuboidal case, and this will be for a generalized one. Now what we essentially can realize is, this is nothing but it is an equation of a straight line, mx plus c, but this c will turn to 0. This c will turn to 0 because when x is 0, then y is also 0. So this means the c will turn to 0. This is a similar treatment that we offered for the elastic region of the linear relation, exhibiting a linear relation between the stress and strain. So the reason why we need to consider all this is because the K is nothing but, in this case, the K in this expression is equal to the M in this expression. So we have an expression relating volume and the dimension along a specific direction, and we have the equation of straight line. So both these are of the similar form. So here V, the volume, is the dependent variable, Lx is the independent variable x, and K is equivalent to M, which is nothing but the slope. Now when you have a straight line, the way of describing the slope is nothing but, so for this case, for the straight line here, the slope is nothing but dV by dLx. So dV by dLx is the slope. So what we essentially then have is K M is dV by dLx. And this K here from this expression, so if you consider this expression alone, this K here can also be estimated as the ratio of V by Lx. So therefore, what we end up having is, so this expression here, 1, from 1 we get this relation, and from 1 and 2 we get this relation. So 1 and 2 we get this relation. So ultimately what we end up having is K, the slope M is equal to K, and this is dou V by dou Lx, and which is nothing but V by Lx. So this is a really important expression in our consideration of how the volume changes. The slope is nothing but the ratio of this dV by dLx is V by Lx. Now this equation 3 we can substitute in our original equation that we have here. So we have change in the volume with respect to the change in the dimension along the specific direction. This change is nothing but the ratio of the volume and the dimension for a given instant and the dimension along that specific direction. So this is the critical expression relation that we can substitute in our relation for the overall change in the volume. Now the overall change in the volume, we have considered the change in the volume with respect to the change in the dimension or in specific directions. So we will be able to get rid of these derivatives, and we will be able to express it as dV is equal to V by Lx dLx plus V by Ly. So whatever we have done for the dimension along the x-axis, the similar treatment can be extended to the dimensions along the y and z axis. So and we will be able to end up with a similar relation, that is dV by dLy is V by Ly, and similarly dou V by dou Lz is V by Lz. So these relations, through similar treatment, we will be able to arrive. Therefore we will be able to substitute all these three relations to our principal expression describing the overall change in the volume. So we will be able to substitute or replace these partial derivatives with the ratio of V by corresponding dimension in the specific direction. So when we do that, we end up with an expression of this sort, dLz. Now in all these three terms we have V that is constant, so we can replace, or we can take this V out, and what we will be left with is change in the dimension along the x-axis to the original dimension along the x-axis, change in the dimension along the y-axis to the original dimension along the y-axis, change in the dimension along the z-axis to the original dimension along the z-axis. Pardon me, there should be a y. So what we have then end up with is three sets of terms, and each of these terms, it indicates the change in the dimension because of the loading that we have imposed along the specific direction, and it is the ratio of this change in the dimension to that of the original dimension along the same direction. So therefore this ratio is nothing but the strain. So all these ratios, they indicate strain along the corresponding direction of x, y and z, and therefore we can replace this expression, or we can rewrite this expression. So this is not a new but V as epsilon x plus epsilon y plus epsilon z. So what we have so far done is, we began by considering the overall change in the volume, and we expressed it as sum of the change in the volume as one of the dimension along a specific direction changes. So we are considering the overall change in the volume, and we have expressed it in a specific way by considering sum of the volume change when one of the dimension along a specific direction changes. Now, owing to the relation between the volume and the dimension in the specific direction, we were able to replace this derivative as the ratio of volume and the dimension in the specific direction. So that helped us arrive at this rather straightforward expression here. And when we take the common term out, the volume term out of the straightforward expression, what we end up with is each of these terms, they indicate the change in the dimension along a specific direction with respect to its original dimension. So which is nothing but our canonical description of strain. So each of these terms, what they indicate is the resultant strain along the specific direction when you impose a triaxial tensile loading. So we have begun with a triaxial tensile loading assumption. We have considered the volumetric change, and the volumetric change we have expressed in a specific format, and owing to the relation between the volume and dimension in a specific direction, we were able to get rid of the partial derivative and introduce a ratio. And when you take out the common term, you end up observing that the overall volume change is the sum of the strains that you observe in the specific direction, the sum of the overall strains. As you can see, these are overall strains. They do not have two subscripts. These are overall strain along the x-axis, overall strain along the y-axis, overall resulting strain along the z-axis. Now, for the triaxial case, we already have arrived at an expression for the overall strain along the x, y and z direction. So let us substitute that. So the overall volume change is the product of the original volume, and now we are substituting the expression for the individual strain that we observed during the triaxial loading condition. So it is 1 by E. So maybe we have to use a different bracket notation to make it more convincing. So yeah, 1 by E. We are now replacing epsilon x with the corresponding load or the stress that establishes it, minus mu sigma y plus sigma z. So this is the expression for epsilon x, and we will have a similar expression for the epsilon y. It's mu x plus sigma z, and a similar expression for the epsilon z. Again, we have considered the form of these individual stress earlier, even in this lecture. So there are common terms. So we this E, the Young's modulus, is a common term. So V by E, and it is also possible for us to rearrange. Once you take the E's out, what we end up having is we will be able to sum these sigma x, sigma y, and sigma z separately, and we can take the the Poisson's effect also. So when you take the Poisson's ratio or the nu here out, then you would end up having these combination of these couple of terms. So it will be sigma y plus sigma z comes from this term here, plus sigma x plus sigma z which comes from here, plus sigma x plus sigma y which comes from here. So the first two terms from here, the second two terms from here, the third two terms from here. I hope there is no confusion at this in this manipulation of the expression. Now what we have is we have 2 sigma y's, 2 sigma z's, and 2 sigma x. So ultimately we can even simplify this expression as sigma x plus sigma y plus sigma z, minus we can take the 2 out, and you will end up having sigma x plus sigma y plus sigma z. Now we can also further simplify this expression, because these three summations of the triaxial load, the triaxial stress we impose, are the same. So therefore we can express this as V by E sigma x plus sigma y plus sigma z, and 1 minus 2 nu. So the overall change in the volume for a triaxial tensile loading, we have an expression for it. Now, it is also possible for us to bring this V down. So, when we bring this V, the overall volume, down or to the denominator of the term in the left hand side, then the expression that results is of this form. Yeah. Mu by E and by 2. So, what I have just done is I have just rearranged these terms, and we now have on the left hand side of your expression of your equation, you have the ratio of change in volume to that of the original volume. So, here when we saw similar expression, that is change in the dimension with respect to the original dimension, we immediately attributed it to strain. Now, here we have change in volume with respect to the original volume, and therefore it is possible, it is reasonable for us to call this as volumetric strain. So, our description of strain, what it means is change in a dimension along a specific direction with respect to its dimension from the original dimension. Now, here what we have is change in the volume with respect to original volume, so it is rather reasonable for us to address it as volumetric strain. So, in the left hand side of the expression, we have the volumetric strain, and in case of the right hand side, what we have is the sum of the stresses that brings about the volumetric strain, and we have certain other terms associated with it. Now, ultimately, it is possible for us to rearrange this expression as well. When you rearrange this expression, it is possible for us to rewrite this as, so we bring this term over here, we bring these terms and these terms over here. So, sigma x plus sigma y plus sigma z. So, we are having in the numerator the combination of all the different stresses that we impose when we are imposing a triaxial tensile loading, and when we bring this term here, we have dV by V. So, we have sum of stresses that contribute to the mechanical condition, and what we also have is the resulting volumetric strain. So, we brought this overall term downwards, and when you do that, what we also end up having is E by V 1 by 2 minus nu. So, E, or rather here, so there should not be any V, pardon me. So, this should be 1, and this also should be 1, because we have brought the V down. So, this should be 1 and this should also be 1. So, ideally what we have now done is we have the summation of all the stresses that we impose and the volumetric strain on the left hand side, and we have certain constants along the right hand side. So, this is 1 and this is 1, so therefore it will be E by 1 minus 2 nu. So, E is the Young's modulus, and this nu is the Poisson's ratio. So, essentially this is the expression that we end up with. So, what we have in the numerator is the overall stress, the sum of all the stress that we impose in a biaxial tensile loading, and in the denominator we have the volumetric strain. Now, when we consider the change in the dimensions along a specific direction, particularly within the elastic region, so again we are focusing on not the overall mechanical deformation, we are not considering the entire mechanical deformation. All our discussion have been thus far confined to the elastic region. Now, when you consider a change in the dimension along a specific direction with and corresponding stress that brings about it in the elastic region, this strain, so if we consider a simplistic case of uniaxial tensile loading, the stress that we impose is directly proportional to the corresponding strain. So, the stress that we impose in the elastic region is correspondingly proportional, or it is proportional to the corresponding strain that we observe within the elastic region. And the constant of proportionality, we know that this linear proportionality is possible because there is a constant of proportionality, that is Young's modulus, that relates the stress and the strain. So, when you have a constant, so when you take the ratio of the stress and strain, and the ratio yields a constant value like we observe under uniaxial tensile loading within the elastic region, when you observe such a relation, when the ratio is of a constant value, then it means the stress that we impose and the corresponding strain that we observe is proportional to each other. Now let us extend the same understanding to this expression here. So we have an expression here. So let us extend the same understanding to this expression here. That is, we have sigma x plus sigma y plus sigma z, the overall stress that we impose during triaxial tensile loading. Then we also have the volumetric strain, and this is equal to E by 1 minus 2 nu. Now E is a constant and nu, a Poisson's effect for a given material, is also a constant. So what this essentially means is that when you have a ratio and the ratio is constant, what it essentially means is the sum of the stresses is directly proportional to the volumetric strain that we observe. So within the elastic region, when you are imposing a triaxial tensile loading, and this triaxial tensile loading, it brings about a change in the volume, the sum of the stresses is directly proportional to the volumetric strain that we observe. So not only does the stress is proportional to the change in the dimension along the specific direction, but the stress that we impose is proportional to the overall volumetric change that we observe in a given system. So whenever within the elastic region, whenever we are imposing uniaxial, biaxial or triaxial loading, the volumetric change that we observe is directly proportional to the stress that we impose. The relation we observe, it reflects the relation we observe between the stress and the change in the dimension along a specific direction. So this way volumetric strain behaves is also the similar way a given strain behaves, a normal strain behaves. So there is a direct proportionality within the elastic region between the stress that we impose on the volumetric strain that we observe. Now it is possible for us, without considering or the specific constants that are involved, it is possible for us to replace this constant of proportionality with another constant. So we are just replacing this proportionality sign here with a constant of proportionality k, and this k, when we compare, when we relate these two, is nothing but this. It is the ratio, so it is the ratio of E and 1 minus 2 nu. This k is the ratio of E and 1 minus 2 nu. The way we introduce this k is because we have treated separately. We have arrived at a relation that shows us the imposed stress is directly proportional, is linearly proportional to the volumetric change, and to remove this proportionality, we introduce a proportional constant, and this constant, now we are able to arrive at an expression for this constant, and this constant is referred to as the bulk modulus. So what we have gained so far, what we have understood so far is, when you impose triaxial tensile loading to a given material, the change in the volume that we observe within the elastic region, when the deformation is elastic, when the distortion is elastic, is directly proportional. So when you want to get rid of, when you want to arrive at an expression, when you want to arrive at a relation, you get rid of the proportionality sign through a constant, and that constant is in the form of the Young's modulus that we have for the common or the generalized or the simplistic stress strain relation. So therefore it is referred to as the bulk modulus, and the bulk modulus can be related to the Young's modulus in this manner, wherein we consider Young's modulus and also the Poisson's ratio. So ultimately, now using the bulk modulus, we will be able to describe how the overall volume of a given material would change within the elastic region when you are imposing a mechanical condition to the material. So we have started with the Young's modulus, and the bulk modulus is also of the same form, wherein the volumetric strain is directly or linearly proportional to the stress. So therefore we were able to replace the volume, so we were able to relate the stress to the volumetric strain through the constant of proportionality. This constant of proportionality is the bulk modulus, and through our derivation we have seen that this bulk modulus can be related to the Young's modulus and also the Poisson's ratio. Now before winding up this lecture, so even though we have got ourselves introduced to a new modulus, or a new way of describing the response offered by the material. So this way of describing the response offered by the material comprises of the entire volume. It considers the entire volume. So before winding up this lecture, I just wanted to introduce you or just wanted to revisit the different mechanical conditions that we have seen. So in the beginning of the lecture, we saw that even though we have considered biaxial, uniaxial, biaxial and triaxial tensile loading, in all these cases, that is uniaxial, biaxial and triaxial, in all these cases, the nature of the load was the same. That is, we have largely been considering the tensile loading alone. So now that we have arrived at, now that we have seen that how for the triaxial tensile loading we can arrive at an expression for the response offered by the material. We know how to derive the response offered by the material for the tensile loading, uniaxial, biaxial and triaxial tensile loading. It is also possible. The reason we consider the derivation of these individual expressions that we have for the change in the dimension along the x, y and z axis for the triaxial loading condition is because we have considered in the last lecture the derivation for it. The primary reason for it is because often there will be combination of mechanical conditions. So it is also possible that along two directions there is compressive load, and along the third direction there is a tensile load that is acting on the material. So when we know how to express these response offered by the material in a generalized case of uniaxial or triaxial tensile loading, and we also know the conventions associated with the compressive loading, we will be able to appropriately manipulate or appropriately arrive at the description for strain along these individual directions. So let me repeat, even though these expressions are rather confined to triaxial tensile loading, if there is a different condition of a biaxial tensile loading and a uniaxial and a compressive loading, or if there is a combination of the tensile and the compressive loading in a different manner, we will be able to rather consistently manipulate this expression to arrive at the response for the strain along these directions. So all we need to do is we need to introduce the appropriate conventions associated with the compressive loading, and we will be able to then consistently derive the expression for the stress along the rather strain along the x, y and z axis, even though the loading condition is not completely uniaxial tensile, but it might be the triaxial tensile. It might be the combination of two tensile load and one compressive, or two compressive load and one tensile. Irrespective of the nature of the mechanical condition, we will be able to manipulate these stresses that brings about the response and arrive at the individual expression for it. So what we have thus far done is we have given a generalized approach. We have considered a generalized derivation which can be manipulated consistently based on the mechanical condition that we observe, the mechanical condition that we desire. So it's not necessary that we are restricted to only the triaxial tensile loading. Any combination of tensile and compressive loading, we will be able to describe the resulting stress from these three expressions here. So with this, we will wind this lecture up, and in the next lecture we will try to find out if there are any other forms of any other nature of loading condition. Goodbye.